Good morning. Today, I will talk to you about an alternative climate change theory that is compatible with the radiative theory. The supporting data is presented in a book that will soon be published in Hungarian, thanks to Laszlo Sarka, a member of this society to whom I am very grateful. The consensus radiative theory is based on radiation exchange at the top of the atmosphere and vertical energy transport. Therefore, small changes in greenhouse gases take on disproportionate importance in this theory, which the evidence has failed to support. The thermodynamic theory of climate change that I present is also based on the greenhouse effect. It is based on two proven and indisputable elements: the big disparity in the greenhouse effect between the equator and the poles, and the variability in meridional heat transport between the equator and the poles. A change in the amount of heat transported between regions with different greenhouse effect must result in a change in the planet's energy emissions, altering the climate system's energy content producing the change in the climate. The greenhouse effect depends 75% directly or indirectly on the presence of water vapor in the atmosphere. It is strongest at the equator, where water vapor concentrations reach 4%, and weakest at the poles in winter, where concentrations approach 0%. The second element of the thermodynamic theory states that energy is transported variably between the equator and the poles in the form of heat. These two elements form the basis of the theory. Most solar energy enters the climate system in the tropics. This creates an insolation gradient that is crucial to the planet's temperature, as illustrated by this figure from Richard Lindzen, a physics professor at MIT who supports the thermodynamic theory of climate change. The temperature remains stable in the tropics, T1, whereas it varies with latitude in the extratropics, T2. In the tropics, temperature depends mainly on the greenhouse effect, whereas in the extratropics, temperature depends on transport. There is a net gain of energy in the tropics and a net loss at the poles. This is compensated by the meridional transport of energy. The planet's temperature variation depends on the change in T1 divided by 2 and the change in the T2 gradient divided by 4. The planet's temperature is anchored by T1, which has changed little over the past half-billion years. Meanwhile, variations between glaciations and the Eocene epoch mainly depend on changes in T2. The greenhouse effect plays an important role in establishing T1, but has little relevance to T2, which is much more dependent on thermodynamic heat transport. When the planet transitions from a glacial to an interglacial period, most of the 5.5 degrees Celsius temperature increase depends on the 20 degrees Celsius increase in T2, rather than the 1 degree Celsius increase in T1. Now, let's look at the second element of the thermodynamic theory. Heat transport must be variable. In the blue curve, we see the change in the planet's temperature excluding the polar regions. The orange curve shows the temperature change in the Arctic in winter, when all the heat comes from lower latitudes because the sun does not shine. Therefore, the changes in this curve are due to changes in transport. These changes cannot be explained by the radiative theory. Only the change between 1997 and 2016 is attributed to Arctic amplification due to feedback from increased greenhouse gases. Now, let's focus on what happened around 1997. I have demonstrated the viability of the thermodynamic theory of climate change by showing that the greenhouse effect differs greatly between the equator and the poles, and that the thermodynamic transport of heat to the Arctic varies over time. Now I will present evidence that thermodynamic changes within the climate system have recently altered the climate. I will present evidence that the Arctic climate shifted in 1997. I will present evidence that this shift was due to a change in thermodynamic heat transport. And I will present evidence that this was due to a shift in the global climate in 1997 that only the thermodynamic theory can explain. As we have seen, the winter temperature in the Arctic abruptly changed around 1997. Since the sun does not shine in the Arctic during this time of year, and heat is transported from lower latitudes, This evidences that the meridional transport of energy abruptly changed around that date. The change also affected the extent of Arctic sea ice, which began to decline rapidly. This has caused great concern because some people believe the decline is due to our emissions causing amplified warming through unmeasurable feedback factors. The Greenland ice sheet also experienced a significant increase in mass loss in 1997. These changes clearly indicate a change in the thermodynamic transport of heat to the Arctic around that time. I will now present evidence showing that this shift in heat transport actually occurred. The Earth's rotation, temperature gradient, and Coriolis effect create a zonal atmospheric circulation that opposes the meridional heat transport to the Arctic. Occasionally, an atmospheric block occurs, stopping zonal circulation and significantly increasing heat transport. Since the turn of the century, the number of blocking events in the Northern Hemisphere has nearly doubled. This implies a significant increase in the transport of heat to the Arctic by the atmosphere. Around the turn of the century, the ocean's transport of heat to the Arctic also increased sharply. This contradicts the widespread belief that changes in atmospheric and oceanic transport cancel each other out. In fact, both grew significantly at the same time in the same direction. Clearly, the increase in heat transport indicates that the climate shift was global, not just in the Arctic. In 1997, the Pacific Ocean shifted regimes, as evidenced by the cumulative index of the Pacific Decadal Oscillation. The cumulative index clearly shows that the Pacific shifted from a climate regime dominated by El Niño conditions to one dominated by La Niña conditions in 1997. The cooling trend in the lower stratosphere stopped in 1997. Since then, the temperature in this region has remained stable. This is important because some argue that cooling of the stratosphere is a fingerprint of anthropogenic warming. As predicted by theory, the decrease in temperature gradient has caused the accumulated kinetic energy of hurricanes and storms to decline since the mid-1990s. This is in stark contrast to what the media tells us. This is a page from my book that explains the 1997 climate shift and an article that identifies a 1998 shift in the frequency of hot days in Europe. Climate scientists are failing to compile evidence of this natural global shift because it does not align with their expectations of anthropogenic climate change. I'm the only scientist who has proposed an explanation based on the thermodynamic theory of climate change. Therefore, the thermodynamic theory has been proven. It is based on two proven assumptions: the greenhouse effect inequality and the variability and meridional heat transport. There is ample evidence that climate change due to thermodynamic causes has occurred in the past and is occurring now. The thermodynamic theory is far superior to the consensus radiative theory because it can explain many climate mysteries that the radiative theory cannot, such as the missing forcing during the Little Ice Age, the possibility of warm, equable climates in the past, the effect of Milankovitch forcing on climate, and the impact of solar activity on climate. Let's start with the Little Ice Age. The intertropical convergence zone is the planet's climatic equator. Heat is transported from there toward both poles. This equator shifts with the seasons according to the planet's needs for heat transport. During the Little Ice Age, the intertropical convergence zone shifted, causing a 1.7 petawatts change in atmospheric heat transport across the equator. This equals 30% of all the energy transported by the atmosphere toward the pole at 35 degrees north. The consensus radiative theory does not recognize any climate forcing that could account for such an energy disturbance. It has been proposed that the 500 kilometers southward shift of the intertropical convergence zone during the Little Ice Age was caused by the cooling of the northern hemisphere due to low solar activity during that period. We will examine this solar effect in more detail later. During the Little Ice Age, the cooling of the northern hemisphere caused the temperature gradient in that hemisphere to increase. This shifted the intertropical convergence zone southward, directing more energy toward the Arctic. This thermodynamic change is not included in the consensus radiative theory. The Little Ice Age cannot be explained by the consensus because it is based on global changes in the greenhouse effect, which cannot explain thermodynamic changes at the hemispheric level that can alter the global climate. Evidence of these thermodynamic changes exists in the data. Solar activity was very low due to a series of grand solar minima. Temperature evolution in southern Alaska has been reconstructed and shows a clear correlation with the solar record, with one peculiarity. Lower solar activity corresponds to higher temperature. This means that Alaska was warmer during the Little Ice Age than it is now. This result is confirmed by ice cover in the Chukchi Sea, which is the entry point for heat from the Pacific Ocean into the Arctic Ocean. The figure shows the inverted ice cover reconstruction. Up indicates fewer months with ice cover per year. Other studies have also demonstrated an inverse relationship between solar activity and temperature in Greenland over millennia. Now, let's move on to another climate mystery: equable climates. These are climatic periods characterized by minimal temperature variation between the equator and the poles, as well as between seasons. This leads to the low gradient paradox because, in order to have warm poles in winter, more heat must be transported. However, the amount of heat transported depends on the gradient, which is small when the poles are warm. According to the radiative theory of climate change, such warm poles would require absurd levels of CO2. We have clear evidence of tropical flora and fauna in the Arctic during the Cretaceous and Eocene periods. Even during the Miocene, forests rich in all kinds of animals covered Greenland. How is this possible if a smaller temperature difference means less heat transport? The solution to this puzzle lies in the first element of the thermodynamic theory: the difference in the greenhouse effect between the equator and the poles. During warmer periods in the Arctic, the humidity was much higher. With the arrival of winter and darkness, a thick radiative fog formed. We see this fog over bodies of water in winter today, and it produces an extremely strong greenhouse effect because infrared radiation cannot pass through it. According to the thermodynamic theory, equable climates are not problematic. Rather, they are evidence that climate change occurs through changes in the inequality of the greenhouse effect between the equator and the poles, as well as through changes in heat transport between the two. Now, let's move on to today's third mystery. According to Milankovitch theory, orbital changes are responsible for glaciations and interglaciations, but they result in changes in insolation that are too small to produce the supposed climatic effects. In fact, they can only explain a small percent of these changes. This is the same problem as with solar variability. However, in the case of Milankovitch theory, this problem is accepted by justifying the climate sensitivities to these small changes as being extremely high. Examining the changes in radiation produced by changes in the axis tilt reveals that they are only significant at the poles. When we add in temperature changes, we see that for 7 cycles of obliquity, there are 7 temperature increases of different magnitudes. There is no 100,000-year cycle. Looking at the peak summer insolation at 60 degrees north, which depends on axial precession, we see that it has 11 cycles that do not always coincide with temperature changes. Now, let's look at the peak summer insolation at 30 degrees north, which is somewhat different but only on certain cycles. The difference in insolation between 60 degrees and 30 degrees is the insolation gradient, on which the temperature gradient depends. This gradient also exhibits 7 cycles. The cycles in the insolation gradient due to precession coincide with the cycles in the axial tilt. We observe 7 gradient cycles, 7 interglacial attempts, 3 successes, and 4 failures. Here, I present evidence that, as with Milankovitch forcing, the changes in the climate system are caused by changes in the meridional heat transport. According to the thermodynamic theory, an increase in heat and moisture transport is required to expand polar ice sheets at high latitudes, not a decrease. An increase in the meridional heat transport and moisture around 1997 led to an expansion of Greenland's summer snow cover. The increase in snow area since 1997 supports the thermodynamic theory, but cannot be explained by the radiative theory of climate change. The last climate mystery I will discuss is the effect of solar variability on the climate. This has been a topic of interest for scientists for 200 years. The IPCC only considers changes in total irradiance. However, as with Milankovitch forcing, these changes are too small to significantly affect the climate. The IPCC is highly confident in this. How can it be confident about something that is poorly understood? Paleoclimate records contradict the IPCC's findings and support that solar variability has a strong impact on the climate. Here, I present a reconstruction of Holocene temperature based on 72 proxies published in the journal Science. I have marked the 7 most prominent abrupt climate changes in it. These changes are well known to paleoclimatologists. I marked the 4 that have 2 special characteristics in orange. They are separated by multiples of 2,500 years. The 14C changes are shown in red. While they are an imperfect proxy for solar variations, we can see that the 14C changes coincide with many of these climate changes, with a few exceptions. The 4 events in orange share another commonality. They all coincide with one of the 4 spur-type grand solar minima of the entire Holocene period. These 4 special grand solar minima all have the same 14C variation profile and an extremely long duration of 200 years. Solar variability affects the meridional transport of energy, and therefore it is explained by the thermodynamic theory of climate change. It is a thermodynamic change, not a radiative one. This nonlinear, indirect mechanism is affected by other factors, making it particularly difficult to elucidate. I will show what happens when solar activity is low. The opposite occurs when solar activity is high. The solar signal is received in the ozone layer, which is the part of the climate system that is most sensitive to solar variability. It acts on the tropical stratosphere, altering the temperature gradient between the equator and the poles, which decreases. The strength of the zonal winds, represented by the circles, depends on the gradient and weakens as it decreases. As the wind strength weakens, it allows an increase in planetary waves, which are atmospheric waves generated in the troposphere that transport energy and momentum. They deposit this energy and momentum in the vortex. This weakens the polar vortex. Some scientific studies have found this effect of solar activity on the polar vortex. For example, one study observed that high solar activity intensifies the strength of the winds that make up the vortex. Therefore, it is not hypothetical but rather observational. A weakening polar vortex allows more heat to be transported to the Arctic. As we have seen, the consequence of increased transport is that the Arctic warms and emits more infrared radiation into space, which cools the planet. Although the thermodynamic theory of climate change is not new, today only a few scientists, such as Richard Lindzen and I, defend it. However, the mechanism by which solar variability affects the planet's thermodynamics is new. I call this mechanism the winter gatekeeper hypothesis because it is based on the regulation of heat entering the Arctic, primarily during the winter. There is ample evidence supporting this hypothesis. The energy necessary for solar variability to affect the climate does not come from the sun itself, but rather from the climate system through planetary waves. In this graph, we see solar activity in red over more than 40 years, and the amplitude of planetary waves in black. These are data from a study. As we can see, the amplitude of planetary waves increases when solar activity decreases. This is consistent with the winter gatekeeper hypothesis's argument. The Earth's rotation undergoes slight changes for various reasons. One of these causes is solar activity, which, to date, no one has been able to explain. The Earth's rotation speeds up in summer and winter and slows down in autumn and spring. These changes are related to the intensification and weakening of the meridional circulation toward the winter pole due to changes in the temperature gradient. When we observe this phenomenon during a year of high solar activity, we see significant changes in the boreal winter component. This indicates that solar activity primarily impacts the meridional circulation towards the Arctic during the winter. Now, let's examine this over a period of more than 50 years. This graph shows solar activity over 5 solar cycles in red, based on sunspots. The black line shows the change in rotation from fall to winter, measured in milliseconds of day shortening. It also shows 5 cycles that generally coincide with solar cycles. The 2 cycles with the greatest deviation are due to 2 strong El Niño events, which are known to affect rotation. The green dotted line is from a 2014 study using all the rotation data. While the IPCC believes that solar variability does not provide enough energy to significantly impact the climate, the evidence clearly demonstrates that it modifies the climate by altering the meridional heat transport. The only explanation for this phenomenon is offered by my hypothesis. Therefore, we can conclude that the thermodynamic theory of climate change is a viable theory based on the differential strength of the greenhouse effect in the variability in the meridional energy transport. It's supported by a large amount of evidence, has a bigger explanatory power than the radiative theory, solving several climate mysteries. Explains the solar effect on climate through the winter gatekeeper hypothesis. Thank you very much for your attention.